morning, everyone. My name is Lee, and I'm here from Korea Research Institute of Chemical Technology. It is located about 150 kilometers south of Seoul. I will present the second topic this morning. Dr. Jong Shik Chung will present the title of phase cooperation of multiphase molybdenum oxides for the propylene oxidations. Dr. Jong got his BS degree from Seoul National University, MS degree from KAIST, and his PhD degree from the University of Connecticut, one of the worst word to pronounce for Korean. And he made his postdoc 84 and 85 from the Northwestern University. And he worked about 3 years at the KIST. And since 87, he's the associate professor of postdoc 4I. Now he's acting as a manager of Division of Chemical Engineering Research Institute of Science and Technology. Please.
Thank you, Dr. Lee, for kind introduction. I'm very pleased today to meet a couple of familiar Korean not United States delegates and unfamiliar delegates. Also, I'm very pleased to be first Korean speaker of this symposium, because there is some problem in Korea saying receiving punishment, not cake or carrot. First is much better than receiving it later. Many industrial chemicals are produced by partial oxidation, and the catalyst used for the partial oxidation is basically composed of either molybdenum or vanadium-based melting components. Since around 1987, the multi-component oxide has been developed so well, I think, and catalyst is optimized very well in industrial field, but in academic field, unfortunately, it's very difficult to start. Unlike metal catalyst, metal oxide semiconductor is changing its surface properties during reactions. As you can see, generally the catalyst, for example here, the propylene oxidation is very complicated. It has molybdenum oxide and all other three kind of transition metals and alkali metals. And a couple of people try to explore the catalyst, how the structure is going on. But all these models, although it's based on spectroscopy, it still is considered as a model because it's not fully based on experimental result. Most recently, Professor Clearov proposed from the Nesborough study, if you have cobalt molybdenate and ferric molybdenate and bismuth molybdenate, three different phases, and reaction occurs mainly on bismuth molybdenate, and oxygen can be solved at ferric molybdenate and moves to the reaction zone, kind of spillovers. And this is well known as a redox mechanism in partial oxidation field. Recently, in last 3 or 4 years, since the multi-component oxide is very complicated, number of people tried to figure out the reaction mechanism by using physical mixtures of a binary oxide. Among those, Professor Delmon is the frontier. He used oxygen 18 isotope and to look at how oxygen incorporate. According to his conclusion, he saw when he incorporate oxygen 18 on antimony oxide, then when he did the reaction, he found reaction products which has oxygen 18, and he knows the reaction site is MO3. So he concluded there's some kind of spillover of oxygen during reaction. So he called this as remote control mechanism. And this kind of mechanism is also supported by number of experiments by Professor Jong. And in this system, they think in donor phase, oxygen potential can solve, and in transport acceptor side, here the hydrocarbon is reduced by taking lattice oxygen. So in this case, they consider only the structural point of view, physical point of view. But in my point of view, the reaction on semiconductor is very controlled. I mean, reaction occurs in controlled way because the free electron in semiconductor is not abundant, and it's kind of controlled reaction. So I have thought there might be some electronic effect by adding one phase to another phase. In case of other papers, what they studied is the donor type oxide, and another type is MO3. In this case, in donor type oxide, you got fast oxidation rate, but the catalyst itself, this phase itself is very active for the partial oxidation reaction, but not selective. It gives the total oxidation product. And the reaction side, oxidation is very slow. It has low activity, but selectivity is very high. So you can naturally assume oxygen spilled over from here to this side to provide oxygen to hydrocarbon. So I selected another kind of the model catalyst. For example, here, alpha bismuth molybdate, I will call this BN. And BN, in case of BN, for propylene oxidation is well known. It's reaction site, and it's active and very selective to produce alpha-line. And it also gives relatively fast oxidation rate compared with MO3. So in case of MO3, it has slow oxidation rate, and the reaction gives the total combustion product. So you can actually indicate assume where oxygen comes from, because this is fast oxidation site, also not only fast oxidation and others reaction site. You can imagine how oxygen from here can move to the reaction site. And so we chose this kind of different system, and we did a number of experiments. For example, here, this physical mixture, you can see the conversion of propylene in case of BM, bismuth molybdate, is higher than pure molybdenum oxide. But in case of physical mixture, you can see the enormous increase in activity compared with the mathematical average, especially at high temperature. But the selectivity stays almost constant unless you put in excess, really large amount of molybdenum oxide. So you can really see the sinus effect in activity. This figure shows selectivity after you assume, since it is a physical mixture, there is two possibilities. One is the reaction site is purely comes from bismuth molecule, and somehow there is some activity increase on the reaction side. And second one is reaction occurs only on MO3, and probably bismuth molecule provide oxygen to MO3. So this is experimental result. If you assume the reaction occurs only on the bismuth moleculated side, since you know the observed conversion, this really follows selectivity of observed experimental result. If you assume reaction occurs in MO3, you can get this kind of selectivity. So from this result, you can conclude reaction really occurs are based on bismuth moleculated side, not MO3 phase. We also have done a couple of TPD experiments. So this is pure molybdenum oxide. This is pure bismuth molecule. These two are physical mixtures. As you can see here, we performed the reaction at the 370 degrees C. Then we flush electric tanks down to room temperature. Then flush with oxygen, and flush with inert gas by increasing temperature. So this is what we got. As you can see here, in case of molybdenum oxide, it does not produce much of alkaline compared with the bismuth molecule. And it produces only propylene and lots of CO2. But in case of physical mixture, you can see lots of increase in amount of alkaline dissolved. So somehow two-phase cooperated to produce more intermediate on the surface, which produces many alkaline. So this is the more detailed profile of the alkaline TPD spectra. As you can see here, the pure bismuth molecule gave us two peaks, alpha beta. And in case of molybdenum oxide, it gives only delta peaks. But in the physical mixture, you can see not only increase in dissolved amount, but also the third new peaks of alkaline, some alkaline intermediate, which can be dissolved during TPD. So, as you can see here, this alkaline for BN is based on bismuth molecule we put in this physical mixture. As you can see here, somehow the alkaline consumption per surface area of BN increases enormously as you put in small amount of molybdenum oxide, and it keeps constant somehow. Okay, so it means just adding small amount of trace amount of molybdenum oxide, you already got enormous amount of increase in consumption of propylene on the bismuth moleculated surface, not molybdenum oxide. And how this kind of increase can be happen? This is also shows the relative amount of increase, amount of increase in both alkaline and the CO2 consumption are dissolved. When you compare with the mathematical average, in case of mathematical average, you have to have 1. So you can see enormous increase of alkaline compared with CO2, increase of CO2. Also, we have done the TPR spectra. In former case, we introduced propylene with oxygen. In this case, we introduced only propylene, and including during temperature increase. So propylene should consume lattice oxygen from either bismuth molybdenate or molybdenum oxide. And this is properly done. In case of alkaline, and only molybdenum oxide gives some different profile. Physical mixture and pure bismuth molybdenate, the curve shape is about the same. So this means reaction really occurs on bismuth molybdenate. And somehow there is some increase in number of reaction sites by adding molybdenum oxide. And CO2 follows the same trend. Physical mixture follows the pure BM pattern. After TPD, we introduced oxygen to reoxidize this catalyst. Even in this case, as you can see here, molybdenum is reached a small amount. And bismuth physical mixture B follows more or less oxidation pattern of pure BN catalyst. Also, as you can see here, the physical mixture is reduced a little bit more than pure BN. So we prepared different kind of catalysts, and the degree of surface reduction has varied value. We introduced propylene at room temperature or 300 for finite period of time. We don't know the surface reduction, but we know this is reduced more than room temperature reduction. So this is just kind of unscaled value. But as degree of reduction increases, there is a maximum in alkaline can be solved on the surface. But also, as you can see, the physical mixtures follows the pattern of pure BN, not NO3. So now we can conclude both reaction and incorporation of oxygen occurs on the BN surface, not MO3. So there must be then no oxygen spillover from molybdenum oxide to BN. And this is also shows the MO5 signal, ESR signal. In case of MO3, there is no increase during the as a function of degree of reduction. But in case of BM or physical mixture, if we reduce more, there is a rough increase in MO5 signal. We think MO3 is also reduced a lot in this case, but it does not show any MO5 signal. This means when you got oxygen vacancy, if you release one oxygen, you have 2 electron trapped on the anion vacancy side. And so it can produce MO plus 4. So in this case, MO3 case, the oxygen anion vacancy side is MO plus 4. So it does not give any MO5 signal. But in case of BM or physical mixture, of course BM, which is in contact with molybdenum oxide, does not reduce deeply to produce MO plus 4. Rather than it stays as MO plus 5. So we think this site is responsible for the consumption of alkaline intermediate. So why the BM site is not reduced deeply to produce MO plus 4? And, we don't know the exact feature, but I tentatively think this happens because when you have two different pairs of metal oxide in contact, we know the BM, bismuth molybdenate work function of BM is higher than MO3. So when this is in contact, the electronic band in BM is bended downward. In other words, electrons, free electrons which are generated during the formation of anion vacancy can flow over to molybdenum oxide, which has deeply reduced MO plus 4. So in this case, oxygen on the BM, lattice oxygen on the BM can be more active and fossil to be reduced more deeply. So it generating more side was resorption of acroline. So we think the only role of BM is to modify electronic properties, not to make oxygen spill over to BM to facilitate oxygen. And so with this model system, we want to show you both the importance of the electronic effect and physical effect. So since time is run out, I just want to show you the other result we made with multi-component. When you have three phases in contact like this, you will have some electronic modification, maybe spill over from first oxidation catalytic molybdenate to bismuth molybdenate. If you have molybdenum oxide in contact, the role of molybdenum oxide to make these particles disperse well on the plane of molybdenum oxide. So it really acts as a playing ground and acts as some performance. It is a playing ground. So it makes playing ground. And another role is the cobalt oxide is to coat bismuth molybdenate as thin layers. So we think between these two, there is some electronic modification. But if we have pale molybdenate, we still don't know. We have to figure it out. There must be some spillover oxygen, both oxygen spillover problem and electronic modification problem. Maybe two functions act together to give highest activity compared with pure or binary or solid oxide. Because adding more component to molybdenum oxide, you got higher activities. Thank you. Thank you very much.
Thank you very much, Dr. Jong. The tab is open. Communications? Yes.
Alex Bell, University of California at Berkeley. If I understand the final interpretation, you believe that bismuth molybdenate sitting on molybdenum oxide modifies the electronic properties of the bismuth molybdenate, what you call the BM phase. Now, the way you arrive at this is through indirect evidence, from what I can understand. But I think there's probably a way to check this directly if you would do X-ray photoelectron spectroscopy on a sample which had a very thin layer of BM on top of the M phase. Have you or anybody looked at that?
No, this is first time this is first time I mentioned about electronic effect. Nobody has mentioned about electronic effect yet, because this is first model catalyst we devised. And since we used powder catalyst, and we did some SPX experiment with powder catalyst, but we didn't see any shift in signal because the degree of reduction is very small, in small extent, and it's very difficult to observe binding edge shift by SPX. Well, I might try with a single catalyst you propose. Thank you.
Okay.
Howard Salzburg, University of Rochester. Are these materials better ionic conductors than they are electronic conductors. You've used an electron transfer mechanism, but alpha bismuth molybdate, for example, is an ionic conductor. And they're very hard. These are materials that are hard to make in a stoichiometric mode. Why do you don't consider the ion transfer or something equivalent to that, oxygen transfer through the oxygen ion transfer?
Okay. Thank you. Yes, sir. People, for that reason, people have considered so far oxygen mobility, not electronic modification, electronic properties, because BM is known, well known, the oxygen mobility is very high. But in our case, we know the mobility of MO3 is not so fast. It's not first-side catalyst oxidation, and the catalyst we choose is alpha molybdate and pure MO3, because there's some report, there's some interaction between alpha molybdate MO3, I mean the molybdate, bismuth molybdate MO3. But in case of alpha molybdate and MO3, there is no phase modification during high temperature heating. It is well known. So we have really the two different phases which is contacted by physical sense, not chemical sense. And another my question is, if you have some physical contact, and then if the reaction occurs by ionic conduction, then there may be some decrease in selectivity, because in the point where two phases contacted, the oxygen concentration must be very high. So there must be some decrease in selectivity. But as you can see here, selectivity really keeps constant until you really put high amount of molybdenum. So I think there might be some occurrence of the ionic conduction effects too, but in our model system, the electronic effect is most important, I think.
Okay. Only one more.
This is Shui from Yugong. You're mentioning about just the electron effect of your catalyst, but my suggestion is that if you want to modify the